So in this problem, we need to show that the relation greater than or equals to on the set of real numbers is reflexive and transitive, but not symmetric. Okay, let us begin. So for this, what we'll do, we're going to consider a relation R. So let R be a relation. R be a relation on the set of real numbers R, defined as, so it's going to be defined as the relation R is going to be a set of ordered pairs A comma B such that A is greater than or equals to B, where A and B are real numbers. So this is going to be a relation. Now R being a relation or R simply means that R is going to be a subset of the Cartesian product of the set of real number R with itself. That's what it means when you say R is defined on some set R. Okay, now we need to show that the given relation R is reflexive and transitive, but it is not a symmetric relation. So let's quickly go through each of the definition. So let's say we have a relation R which is on the set A. Then R is going to be a reflexive relation if and only if the ordered pair A comma A belongs to R for all values of A belonging to the set A, meaning any element that we pick up from the set A, and it has to be all the elements actually, or for all the elements that we pick up from the set A, if the ordered pair A comma A belongs to the relation R, then we can say that R is a reflexive relation. Then R is going to be a symmetric relation if the ordered pair A comma B belongs to R, implies that the ordered pair B comma A also belongs to the relation R for all A comma B belonging to the set A. And then finally, we have the relation R that is going to be transitive if the ordered pair A comma B belonging to the relation R and B comma C belonging to the relation R would imply that the ordered pair A comma C also belongs to the relation R for all A, B and C belonging to the set A. Okay, so let's check for reflexivity. So here what we'll do, we are going to consider an arbitrary element A. So let's say A, B and arbitrary element such that for A belonging to the set of real numbers R, if we consider the ordered pair A comma A belonging to the relation R, this must imply that A must be greater than or equals to A. According to the definition, all we have done here is replace B with A. So A is greater than or equals to A. So that is what our definition is telling us. But we now have to check whether if this is a true statement or not. Yes, A is going to be greater than or equals to A. This is a true statement which implies that R is reflexive. So R is a reflexive relation. Okay, now we'll check for symmetric. So here we are going to consider two elements A comma B. So let's say A and B are two elements that belong to the set of real numbers R such that if we consider the ordered pair A comma B belonging to the relation R, so this implies that A is going to be greater than or equals to B. This is the definition, but the converse is not true. If A is greater than or equals to B, then B cannot be greater than or equals to A. So here, since B is not greater than or equals to A, this simply means that the ordered pair B comma A cannot belong to the relation R. So this is not satisfying the definition of symmetry. So we have the ordered pair A comma B belonging to R. This must imply that B comma A also belongs to R. However, we are getting B comma A not belonging to R. So here we can say hence a relation R is not symmetric. This is not a symmetric relation. Okay, now coming to the third one where we check for transitivity. So here we're going to consider three elements. So let those three elements be A, B and C. So let A, B and C be three arbitrary elements, three arbitrary real numbers, such that if we consider the ordered pair A comma B belonging to the relation R and we can consider the ordered pair B comma C belonging to the relation R, we must be able to show that A comma C also belongs to the relation R as well. That means we must show that A is greater than or equals to C. Okay, so what does it mean when we say that the ordered pair A comma B belongs to the relation R? This simply means, according to the definition, that A is going to be greater than or equals to B, and the ordered pair B comma C belongs to R means that B must be greater than or equals to C. Okay, now if we combine these two statements, then A is going to be greater than or equals to B and B is going to be greater than or equals to C. So we can also say that A is going to be greater than or equals to C. Now A greater than or equals to C simply means that the ordered pair A comma C belongs to the relation R. So here what we have shown that R is transitive. R is a transitive relation because we started out by considering two ordered pairs A comma B and B comma C belonging to the relation R, and we are able to show that A comma C, this third ordered pair, also belongs to the relation R. So here we have finally verified that the relation greater than or equals to is going to be a reflexive and a transitive relation, but it is not going to be a symmetric relation. Hence proved.